Hello, I'm Alex Howe, and this is the Science Meets Fiction Exoplanets review for December of 2022. And regretfully, I must inform you that this will be the last Exoplanets review video. I'm not leaving the concept behind. Beginning in January, I have started calling out notable exoplanet papers on my Twitter and Mastodon accounts, so you can follow me there if you want to know the latest in exoplanet science. But I decided that I need to drop the video series. It was fun for the first few months, but then when summer came, my schedule changed, and I also had other videos I wanted to make, and making these videos was just too much of a time drain. I liked the idea, I still like the idea, but I just don't have the resources to put into them that they need. So I'm scaling back to covering exoplanet news on Twitter and Mastodon, and that does have the upside that the news will be more up-to-date. Most of the papers I talk about there will be the same day they came out, or at least the same week. But since I couldn't really do that for the previous month's videos that would go in the video series, I needed to make one more of these videos to cover the final month of last year. So let's get to it. There were a couple of interesting papers that affect the overall state of the field. This is probably the most surprising one. The standard RV equation uses omega p, not omega star. And this may be pretty esoteric to many viewers. We don't usually talk about the details of the orbital mechanics when looking at radial velocities of planets. It's just about their mass and orbital period. But the radial velocities do tell us other things. And one of them is omega, which is the argument of periastron. And you can look that up, but the short version is, it is the angular location of closest approach to the star relative to the orbital inclination. And what Householder and Weiss discovered is that a popular computer code for measuring radial velocities had an error in its documentation. It said it was using omega star when it was really using the more appropriate omega planet. And this is just saying, because we're looking at radial velocities, which are the orbital motion of the star, we don't usually think of it that way, but the star moves in a very small orbit as a reaction to the planet's movement. So we're more directly measuring the star's orbital parameters, but we want to know the planet's parameters. And that's where the mix-up comes from. So when we do that, we essentially measure the star going the wrong direction. And this affects about 20% of radial velocity planets. It doesn't affect most aspects of the orbit, so mass, orbital period, eccentricity, inclination, all of that's correct. But it means we're constructing the orbits rotated 180 degrees from their correct orientation. And this is significant because it could cause confusion when we're trying to look at transits of planets known from radial velocities, there are a few of those, or phase curves where we observe the planet all the way around its orbit, and the phase of the planet changes in a way we don't expect. So it's not a huge deal, but it is something astronomers will have to double check when they're looking at radial velocity planets in the future. The other paper I had in this category isn't really a science paper at all, but it will be very useful for science. And this is Trexo Lists, Transiting Exoplanets List of Space Telescope Spectroscopy. And this is simply a central repository for all of the data we have about transiting planets that have been observed with space telescopes. That's mostly Hubble and JWST, but there should also be a few others like Spitzer. And this is really convenient because it can be hard to sift through either a paper repository or the data archives to find all of the relevant data if you're looking at a planet like GJ436b that has been observed many times. Or I've had this problem with brown dwarfs, looking for all the objects that have been observed of a given type. And this repository here will be very useful for putting together those kinds of comprehensive data sets. So that was a nice addition to the field. one interesting new planetary system from December, and this one actually confused me a little bit. This is GJ1002, or 1002, two temperate Earth mass planets. And if this photoshopped image looks familiar to you, it's because I covered a very similar paper in September on the star LP890-9. It was also a red dwarf star that hosted two Earth mass planets in or near the potentially habitable zone. But I had to check a couple times to make sure this is a different star and a different detection method. These planets were found by radial velocity, not transits. And the inner of the two planets could be Earth-like with a sufficient greenhouse effect. Its equilibrium temperature is 231 Kelvin, which is well below freezing, that's 273. But Earth's equilibrium temperature is 255 Kelvin before you account for the greenhouse effect. So with a bit of a stronger greenhouse effect, GJ1002b could be potentially habitable. Although, especially for red dwarf planets, that's kind of up in the air. I found a broader selection of papers looking at studies of planet populations. The first one was this statistical analysis of the dearth of super-eccentric Jupiters in the Kepler sample. And this is really more verification, but verification is something we need to do in science. And basically, we're looking at planets that are in the process of becoming hot Jupiters by migrating inward from more distant orbits via planet-planet scattering. So two giant planets pass close to each other. One of them is potentially ejected from the system, while the other is thrown into an elliptical orbit that brings it near the star, which then becomes circular through tidal interactions. The thing is, those kinds of migrating planets should appear in the blue region on this plot, and we see very few of them. Even though they should pass through it pretty quickly, far fewer than would account for the hot Jupiter population, or even the moderately eccentric Jupiter population. And this paper was really just running simulations to test whether that is real or just a statistical fluke, and they determined that it's real, and that suggests that this high eccentricity planet-planet scattering is not the dominant mode of formation of hot Jupiters. Hot Jupiters can also migrate through interactions with the disk, which keeps their orbits more circular. And I've talked about that in several previous episodes. There's still a lot of conflicting data on that question. So that's one more piece of that puzzle. Next up, orbital structure of planetary systems formed by giant impacts, stellar mass dependence. And this is related to things like the moon forming impact on Earth, but we think that there's a giant impact phase in most young planetary systems, and the moon forming impact is the only one we have clear evidence of in our solar system, in part because it was probably the last one, and of course that would erase any evidence of earlier impacts. But we think that terrestrial planets like Earth form by having many protoplanets that are moon-size, Mars-size, or even close to Earth-size in the solar system after the gas disk dissipates, which the gas disk dampens migration and chaotic interactions. And after it dissipates, the protoplanets will gravitationally scatter until they go through enough giant impacts to merge into a smaller number of final planets that are in stable orbits. And Hoshino and Kobuko ran simulations of planet formation around stars of different mass and looked at the average number of planets produced. And interestingly, low-mass stars produced fewer but larger planets. And that's because around low-mass stars, the zone where you would form rocky planets inside the ice line is closer to the star, so even though the star is lower mass, they're deeper in the gravity well, so this gravitational scattering has a stronger effect. So for the smallest planets, we expect to have an average number of planets produced of 4, which is very interesting because TRAPPIST-1 is in that category, and it has 7 planets, so there seems to be quite a large spread. And then for the largest stars, twice the mass of our sun, the average number of planets is about 12 in these simulations. So that'll be an interesting line of research to follow up in the future. And then we have this paper by Johin Chakraborty and exomoon hunter David Kipping, Transit Duration and Timing Variations from Binary Planets. Now, a binary planet, often called a double planet in science fiction, is usually defined in the literature as two planets orbiting a barycenter that is outside of either of them. So the Earth-Moon system does not qualify because our barycenter is about a quarter of Earth's radius below Earth's surface, but the Pluto-Charon system does qualify. And there are some problems with that definition, but it's the most common one. To date, no binary exoplanets have been found, but there are several probable ways to form them, and the Pluto-Charon system is evidence that modestly sized bodies can easily form them. So Chakraborty and Kipping looked at how detectable they would be, and perhaps unsurprisingly, they found that binary planets would be as detectable or more detectable than exomoons. The length of a transit, because there are two binary planets separated from one another, would be longer, and the amount longer would vary by their orbital configuration, so that could vary by hours. And the timing of the transit could also vary, because the onset and offset of the transit would be at different times relative to the barycenter of the two planets. So, not exactly a surprising result, but we need to quantify these things to get better at looking for these kinds of objects if they're out there. Moving on to theory papers, we had one about sub-Neptunes, the Runaway greenhouse on sub-Neptune water worlds, and this was looking at the internal structure of sub-Neptunes, assuming they have significant amounts of water. And the usual model is you would have a liquid water ocean over top of high-pressure ice, and that'll come up again later. Ice that's under high pressure has a different crystal structure, so it sinks in water. And then a water vapor and possibly partly hydrogen atmosphere on top of that. But with that much water vapor in their atmospheres, they would have a very strong greenhouse effect on these planets, and in fact a runaway greenhouse effect. And Pierre Humbert looked at the internal structure of sub-Neptunes under the influence of this greenhouse effect, and found that it would not be a liquid ocean on top of ice. It would instead be a supercritical steam atmosphere. And a supercritical fluid is something that has properties of both a liquid and a gas, and doesn't really transition to ice except at much higher pressures. And this is important because other studies have shown that a supercritical steam atmosphere would have a significantly larger radius than a regular water vapor atmosphere over a liquid ocean. So that could explain the radius distribution of sub-Neptunes, where water worlds previously weren't so much of a solution to the problem of the evaporation valley. Figuring out the evaporation valley and where water worlds fit into it has been a growing topic of research in the past couple years, and this could be a pretty big clue if we can put it together with some of the other studies. And of course, the gold standard would be JWST observations. So keep an eye out for that. Now, the other interesting theory paper was the nominal range of rocky planet masses, radii, surface gravities, and bulk densities. And this was a paper where I wasn't entirely sure where they were going with it, but it turned out to be potentially very important. So this is debuting the Exoplex code, which is an improved method to calculate exoplanet masses and radii from detailed models of geology and geochemistry. And I thought this was going to be kind of pointless, honestly, because I've worked on papers like this, and changes in geology and geochemistry are such a small effect on radius that it's lost in the noise of error bars from observations. But it turned out to be very important because with this code, they can look at exactly what the interior structure of a planet of a given mass would be, and the range of possible interior structures with plausible compositions. And this is much fancier than just saying 100% rock, 30% rock, 70% rock, 100% iron. No, they looked at what specific compositions are likely to occur, and derived precise limits on what they call the nominal rocky planet zone. I would actually call it the likely rocky planet zone. And it kind of takes some of the guesswork out of plots like this, where you're trying to figure out, would a planet on the edge of this zone be rocky or a water world or a sub-Neptune? This code can put precise probabilities on it. So if that's borne out by future tests, that could be very useful. Now, moving from theory to observations, the newest paper is characterizing notable planets, and the first one is actually closely related to this problem of, is it rocky? Evidence for the volatile rich composition of a 1.5 Earth radius planet. This is Kepler 138d. It's 1.5 times Earth's radius, 350 Kelvin, so pretty hot. Not as hot as Venus, but a lot hotter than Earth. And the interesting thing here is that we usually assume that planets less than 1.7 Earth radii are rocky based on the location of the evaporation valley. However, that is just statistical. It's not a hard correlation. And radial velocity measurements of Kepler 138d show that it has a relatively low mass of 2.1 Earth masses. And when you plot that on the mass radius diagram, you find that it is too large to be rocky. Conclusively too large to be rocky, even going by the 100% rock line. And actually suggests that it is a water world. Not in the sense of 50% water, like outer solar system moons in our solar system, but in the sense of 10% water. And the other alternative is 0.01% hydrogen, which is such a small amount of hydrogen you'd expect it to just evaporate away. So a 10% water composition by far makes the most sense for this planet. And there are an increasing number of planets in that category these days. And I think this one is some of the most solid evidence I've personally seen for a population of water-rich planets at short periods, contrary to the original interpretation of the evaporation valley, which is why we've brought back the water world idea. I don't talk a lot about hot Jupiters because they're kind of the low-hanging fruit of planet characterization, but there was an interesting paper on WASP 43b. And this is a hot Jupiter that has been relatively well mapped out with telescopes. It's hot enough to see the variation in infrared brightness from day side to night side, and we can model that as having a day side temperature about twice as high as the night side. And at that 1500 Kelvin temperature on the day side, we would expect there to be silicate clouds in the atmosphere. And clouds frequently mean variability, because clouds can change over time and they can be patchy in some places or at different levels. So if we look at phase curves of the planet over its orbit several years apart, we can potentially see that variation. But in fact, they did not see any variation. Or rather, they saw some, you can see some in this plot, but they determined it was not statistically significant. So that suggests that there's relatively little variability in the clouds of this planet. Next, we have transit depth variations reveal TOI 216b to be a superpuff. And this was an interesting one for a couple reasons, but the first one was that I had not seen transit depth variations before. Transit timing, transit duration, of course, but not depth. But it's actually pretty simple. It's something that works with grazing transits and orbital precession. And maybe you could make it work for non-grazing transits with limb darkening, but that would be much harder. But this idea of grazing transits is something we have seen before with the first known circumbinary planet, Kepler 16b. Kepler 16b's orbit is tilted relative to our line of sight. And when we first observed it, it was just grazing the second star, and only part of its disk was passing in front of the second star. And over time, its orbit precessed, so it was no longer in the line of sight, and it stopped transiting the second star, and eventually even stopped transiting the first star, just because it's at a slight angle. And it will start transiting again as seen from Earth in 2042. And the same principle applies to TOI 216b, except in this case, the transits were moving onto the disk of the star. It was just skimming the edge at first, but as it started transiting more completely, we were able to get a measurement of its radius. And that was also rather interesting, because this is a Neptune mass planet, but its radius is about twice as large as Neptune's. And that makes it very low density and a superpuff, but it's unusual because superpuffs are usually lower mass, and we don't normally see such large radii for a planet in this mass range. So that's something to examine more closely for its own sake. And then we had this paper on Hubble spectroscopy of L9859C and D, no evidence for clear hydrogen-dominated primary atmosphere. And this is one of those that's honestly a little frustrating to me, because we can take a spectrum of a planet, and for a low-mass planet, it's usually flat. And a flat spectrum means that either it has a high molecular weight atmosphere, like water vapor or carbon dioxide, with very little hydrogen, or there's a high-altitude cloud layer that's blocking out the light. And the only thing we can clearly rule out is a cloudless, hydrogen-dominated atmosphere. And we've been ruling out cloudless, hydrogen-dominated atmospheres for the past 12 years, including my first paper on GJ1214b. And we're hoping to do better with JWST, and we have for a couple of planets, but we're still waiting to get most of the data from that. And the other thing about this paper is that if you look at the spectra, they're not completely flat. They're still statistically pretty close to flat, but there's some evidence for something going on there. Certainly more than for GJ1214b. And in fact, I recently remarked on Twitter about a paper from last week about L9859C, which did a more careful analysis of this dataset, and found limited evidence for H2O and CO2 in the atmosphere. But that was still not really statistically significant, so it was not conclusive. And we need more precise observations to be sure of it. And finally, we had a couple of interesting papers on habitability, as is frequently the case in unexpected places. First, liquid water on cold exo-Earths via basal melting of ice sheets. And this is looking at how likely an ice world is to have an under-ice ocean versus just freezing solid. And also, they didn't really talk about it as much, but it also gets at the question of whether a water world would be able to have minerals in its ocean, because the issue is minerals have to come from the crust, but we're coming back to that high-pressure ice problem again, where the bottom of the ocean is under such high pressure that it will compress into a form of ice that's heavier than water and lock away all the minerals in the crust below it. But this paper suggests that the bottom of the ice layer next to the crust could actually melt due to heat flux coming from the interior of the planet. And if there's melt underneath, then much like volcanoes on Earth, you could have that water seep upwards into the main ocean. And again, they don't really talk about it in the paper, but it could potentially carry minerals and organic compounds up from the crust with it. And they made models of what the composition of the column would be over time. And you can see on the lower left in this plot, even in a column that starts out frozen solid, with just different kinds of ice, you could have a liquid ice layer form in the middle of it over a few million years. They also determined that one of the larger super-Earths in particular, LHS 1140b, is quite likely to have enough heat flow to start this process. And finally, terminator habitability, the case for limited water availability on M-dwarf planets. So there's an interesting thing about how M-dwarf planets are talked about in pop science. Not all the time, but a lot of the time. Which is, we know that a habitable planet around an M-dwarf will probably be tidally locked. And the usual pop science explanation is that the day side will be too hot for life and the night side will be frozen, and so life could only exist along the terminator. But that's not how it's usually addressed in the literature. In the literature, we usually look at the middle of the day side, what we call the I region. Because if you move the planet just a little bit farther out, then the day side will be a comfortable temperature. And that's maybe a better arrangement for habitability. And also, this idea of a frozen night side is not necessarily true, because a thick atmosphere can recirculate heat to the night side and keep it from freezing. But this new study looks at the possibility that there is a large temperature difference, and that could happen if the planet is very water poor. Because if it's water poor, there are fewer volatiles to circulate heat around the planet, and the night side could freeze out more easily. And in fact, even if the night side partially freezes out, it could be a cold trap for water to get stuck there, which could deplete the planet of water over time, which would then lead to only the Terminator being habitable. This is one of many ideas of what's going on with habitability of M-dwarf planets, but this team did a bunch of simulations, and you can see in the plot on the right, the water-rich planets, which are marked with AQ, have much smaller temperature difference than the land-rich planets marked with L between dayside and nightside. So this seems to be a plausible model, and one that we'll want to take a closer look at if we get interesting results from TRAPPIST-1. And that's it for the final Exoplanets review video. Once again, you can follow me for more exoplanet news on Twitter and Mastodon at SciMeetsFiction, and stay tuned to my YouTube channel because I will be making other videos on math and science type topics, hopefully in the near future.